Welcome back to the session of turbo machines. In this session now we will be looking on to centrifugal compressors. Before looking on to centrifugal compressors, we need to understand that the turbo machines are classified into two categories. One is a power generating machine, another one is a power absorbing machine. In case of power generating machine, we will come across various turbines. In case of power absorbing machines, we will come across few of the machines to which mechanical energy has to be supplied as an input, and we need to expect fluid energy as the output. Such machines are called as a power absorbing turbo machines. Examples for those power absorbing turbo machines are fans, blowers, compressors, etc. These are the devices which are going to rise the pressure of the fluid with the expense of mechanical energy. Out of those power absorbing machines, one such power absorbing machine is a compressor. Compressor is the device which is used to compress the fluid, or in other words, it is used to rise the pressure of the fluid. Now, based on the action of the device, compressors are classified into two categories. If the action of the machine is reciprocating, then I will call the compressor as a reciprocating compressor. If the action of the machine is rotary, then I will call the compressor as centrifugal compressor. There, one of the term plays a huge role, centrifugal. Centrifugal in the sense throwing the object away from the center. Here I am dealing with the fluid. Centrifugal in the sense throwing the fluid away from the center. So this centrifugal action is going to compress the fluid, is going to rise the pressure of the fluid. So because of that, I am calling the device as the centrifugal compressor. The action of throwing the fluid away from the center is going to rise the pressure of the fluid. It is going to rise the fluid energy. Such a device is considered as centrifugal compressor. We need to be very clear that these power absorbing turbo machines are going to handle compressible fluids, wherein the density of the fluid will continuously change. So this one aspect we need to keep in our mind. So now we have understood what is a centrifugal compressor. Now I have listed a few of the basic components of centrifugal compressor, such as inlet casing with convergent nozzle, second one impeller, third one diffuser, and the fourth one spiral casing. The sketch of the centrifugal compressor is shown in this figure. We need to observe all these four components in the figure, and we need to understand how these components are going to work. What is the role that will be played by all these components in order to run the centrifugal compressor. So now the first thing is inlet casing with convergent nozzle. Inlet casing in the sense the enclosed area through which the fluid enters, fluid has to pass towards the machine, that is what is inlet casing. Next, with convergent nozzle, we know the nozzle function. Nozzle is the device which is used to rise the kinetic energy of the fluid, I mean velocity of the fluid. So here convergent nozzle, they are specifying it as a convergent nozzle. Convergent in the sense the cross sectional area is gradually decreasing. Such a decreasing area is going to rise the velocity or kinetic energy of the fluid. So very first device is convergent nozzle through which the kinetic energy of the fluid will be raised. So make sure the function of the nozzle is to rise the kinetic energy. This is kinetic energy increment. So this is the first device through which the fluid will be passing. Next, impeller. Here we need to understand the term impeller. Impeller is the device which is used to impel the fluid. Impel in the sense it is nothing but lifting, or we can say rising the pressure. So the device which is solely responsible for rising the pressure of the fluid is called as the impeller. Lifting action or rising the pressure, that is what is impelling action, and the name of that device is impeller. In the machine, in the centrifugal compressor, we knew one of the part of the centrifugal compressor is rotary part. That rotary part is nothing but impeller. So this impeller consists of radial vanes and it is continuously in motion. As soon as the fluid comes with huge kinetic energy from the nozzle, this strikes the blades of the turbine, and this blades of the impeller. This impeller is rotating with very high velocity, and this is going to cause the centrifugal action. It is going to throw away the fluid away from the center. So that is what is the action of impeller. It is going to throw away the fluid from the center. So that is the second part through which the fluid will be passing. Next, diffuser. We knew in the nozzle the kinetic energy has been increased. With this kinetic energy the fluid has entered into the impeller, and then it has subjected to centrifugal effect. Then this kinetic energy does not absorbed or does not increased by impeller. The part of the energy that is developed or kinetic energy with which the fluid is thrown from the impeller has to be regained. In the sense, the fluid is moving away now. The fluid is moving away with the help of kinetic energy. The fluid which is going towards the storing device, the fluid which is exiting the compressor is carrying certain amount of kinetic energy, but I do not need kinetic energy at the end, at the exit. I need compressed energy, high pressure. If the fluid is carrying certain amount of velocity at the exit, then in order to regain that kinetic energy and convert that into the pressure energy, whatever the energy which is going into the exit as a kinetic energy, that needs to be converted into pressure energy. In order to convert that kinetic energy into pressure energy at the exit portion, we need a device called diffuser. So diffuser's function is to convert kinetic energy into pressure energy, which is opposite to that of nozzle. Next, spiral casing. Spiral casing is the casing which is provided at the outlet part of the compressor to provide the proper channel towards the storage device or towards the exit. So that is what is the final casing. So these four are the very important parts that we can observe from the figure, and these four are the parts which plays a huge role in rising the or in lifting the pressure of the fluid. Here I have denoted certain numbers for impeller as well as diffuser. These numbers plays a huge role. 1 is the inlet to the impeller, 2 is the outlet of the impeller. The same 2 is the inlet to the diffuser, and 3 is the outlet of the diffuser. I will be making use of these states or these numbers in future equations. 1 stands for inlet to the impeller, 2 stands for outlet of the impeller. Again the same 2 is also inlet to the diffuser, and 3 is outlet of the diffuser. I will be making use of these numbers when I deal with few of the equations. So this is what is the basics with which the centrifugal compressor works. Okay, let us look on to the few of the terms with respect to the centrifugal compressor. Very first one is slip, next one is slip coefficient. In order to understand the slip and slip coefficient, we need to have a certain theory with us. So what we have understood till now is in the proper passage wherein there is no disturbance in the passage, what we have understood is the velocities are not disturbed, but actually the velocities will not be constant over the time. There will be variation in the velocity of the fluid. If that variation is present, because of that uneven velocity, there will be the uneven pressure distribution. If the velocity changes, since we are dealing with the compressible fluid, I need to keep that in mind. If the velocity changes, then pressure distribution is also going to change. Since velocity and pressure are going to change, there will be the reduction in the head that has to be obtained at the end. What do you mean by reduction in the head? It is nothing but the reduction in the pressure of the fluid at the exit. That is going to happen because of reduction in velocity as well as reduction in pressure. So reduction in head is going to happen. Because of that, I have two of the conditions. One is Euler's head, I have denoted it by H suffix E. Another one is ideal head, which is denoted by H suffix I. What you mean by Euler's head? It is head without slip. If there is no slip, what is actually slip? I will define it. If there is no slip in the fluid, then I will call it as a Euler's head. If there is a slip in the fluid, then I will call it as a ideal head. Please keep these two things in mind. I will be back to that by understanding what is slip. Slip is a difference between Euler's head and ideal head for ideal velocity triangles. It is the difference between Euler's head and ideal head. Now try to understand. Euler's head is the head without slip. Euler's head is the head without slip and ideal head is head with slip. This slip is also defined as Vu2 dash minus Vu2. Vu is nothing but the tangential component. Suffix 2 is nothing but the tangential component of the absolute velocity at the outlet. So, tangential component of the absolute velocity at the outlet minus the same thing with the dash. So, dash indicates that without slip, without dash indicates that with slip. So, without slip minus with slip. Here also it is without slip minus with slip. Without slip minus with slip, without slip minus with slip. So, that is what is the slip, in the sense there will be the reduction in the velocity. Please look onto these two terms. The tangential component at the outlet is getting reduced because of certain slip. That reduction in the velocity itself is termed as the slip and it is denoted by S. Without slip, with slip difference itself is called as the slip, actual slip. So, now head without slip is Euler's head and head with slip is nothing but ideal head. By keeping these two in mind, I will define slip coefficient, which is denoted by mu. Mu is nothing but ideal head Hi, ideal head with slip divided by Euler's head without slip. Euler's head without slip, Hi divided by He. Here in the difference, Hi is the lowest value, He is the highest value. Here also it is the coefficient, lowest value by highest value. I am going to get certain value which is less than 1 for the coefficient. Or other words, in terms of velocities, the mu coefficient can be defined as Vu2 divided by Vu2 dash. Vu2 dash is without slip, Vu2 is with slip. The ratio is going to get me the value which is lesser than 1, because Vu2 is the lesser. Look onto the equation, largest value minus smallest value. Largest value is in the denominator, lowest value is in the numerator. So, this ratio is considered as the slip coefficient and it is denoted by mu. Please make sure with slip values will be in the numerator, without slip values will be in the denominator on either definition. It is Euler's head to the, ideal head to the Euler's head and Vu2 divided by Vu2 dash. Vu2 dash without slip, Vu2 with slip. So, these are the few terms which causes significant role in obtaining total work done by the compressor or in obtaining energy transfer by the centrifugal compressor. Wherever I will be writing the equations with respect to energy transfer or total work done, I will be making use of slip. Till now I have not considered slip in any of the equation. Even while deriving the Euler's formula, U2 Vu2 minus U1 Vu1 or U1 Vu1 minus U2 Vu2, I have not considered slip. But now, from now onwards, this slip plays a huge role in defining the work transfer or energy transfer. Wherever I will be coming across the energy transfer equation, in all those situations I will be including the term which is nothing but slip, the reduction in the velocity due to the slip factor as well as slip coefficient. Okay, let us look on to few of the other terms now. The first term is surging and the second term is choking. In order to understand these two terms, I need a centrifugal compressor characteristic curve at constant speed. When the machine is running at the constant speed, this curve has been taken. On the y-axis, overall pressure ratio is there. Overall pressure at 0.3 divided by overall pressure at 0.1. 1 stands for impeller inlet, 3 stands for diffuser exit, and on the x-axis we have mass flow rate. So, now let us try to understand what is this surging means. At low flow rates, when the flow rates are decreased, the momentary fluctuations in the head or unsteady flow or unsteady discharge of the fluid flow reversal as well as vibrations. These are all the things which may happen at low flow rates. If this is happening at low flow rates, then that phenomenon is considered as surging. So how these things are going to happen at low flow rates, that is the question. In order to understand that, I have plotted this characteristic curve. Now let us say the compressor is operating at point number C, any arbitrary point C, or else you can take point D also, it does not matter. I will take point C. Now what I have to do is, at the exit I have the delivery valve. I will close the delivery valve to certain extent. If I close the delivery valve, the delivery of the compressed fluid is, mass flow rate of the compressed fluid is little bit reduced, because I have closed the valve. Once I have closed the valve, the pressure at the outlet part, the pressure at the downstream is going to rise because of lesser amount of fluid which is entering into the outlet path. So that pressure rise is considered as B. Huge pressure rise is going to happen at the downstream. If I still close the delivery valve, huge amount of fluid will be accumulated at the exit than that of the inlet, because the delivery valve is getting closed. Because of that, entry is lesser and exit is more, and hence huge amount of pressure rise is going to happen at the downstream. If I still close it by certain extent, then it is not going to rise the pressure, overall pressure. Instead of that, it is going to decrease it. What is happening? For closing the delivery valve through certain extents, the downstream pressure is getting increased from C to B and B to A. Once huge amount of pressure is accumulated at the downstream, this downstream pressure is higher when compared to that of original pressure at the inlet. So because of this pressure difference, downstream pressure sides fluid is going to reverse, because the pressure is very high at the downstream than that of the initial incoming fluids pressure. So because of that, flow instead of moving from left to the right, the fluid starts to move from right to the left. From upstream to the downstream. Instead, it is moving from downstream towards upstream. So that is what is going to happen, and suddenly the fluid will take the pressure from A to C or D again. Again the same thing will repeat. It will take the C, if I close the valve, then B, then A. From then A, it is suddenly jumps into the C or D. So this phenomenon of rising the pressures at the downstream because of any irregularities in the flow passage is going to lead to fluctuations or vibrations or unsteady distribution or unsteady delivery or flow reversal. So all these things are the reasons, all these things are the effects of the variation in the pressure, and this phenomenon is considered as surging in centrifugal compressors. So at low mass flow rates, these are the things which may happen, and these things are considered as surging. Next thing is choking. I will take the example of the same sketch. Here choking in the sense, fixed mass flow rate is going to occur irrespective of any pressure ratios. Once certain pressure ratio has been reached, beyond that pressure ratio, the mass flow rate is not going to vary. The fixed mass flow rate is going to happen through the centrifugal passage irrespective of any pressure ratio. Such a phenomenon wherein mass flow rate is fixed irrespective of that of pressure ratio. This is the pressure ratio. Irrespective to this pressure ratio, what is the mass flow rate which is happening? That is the constant mass flow rate. Such mass flow rate, constant mass flow rate irrespective of that of pressure ratio is called as choking. So this is what is surging, and mass flow rate, constant mass flow rate through the passage of the centrifugal compressor is considered as choking. So these two are the very important concepts with respect to the centrifugal compressor. Okay, let us look onto the few equations. Very first equation is energy transfer through the centrifugal compressor. Energy transfer has to be usually extracted with the help of the Euler's equation, wherein Euler's energy transfer equation without slip is given by E is equal to U2 VU2 minus U1 VU1. Since it is a power absorbing machine, E is equal to U2 VU2 minus U1 VU1. If it would have been the power generating machine, then U1 VU1 minus U2 VU2. Since it is a power absorbing machine, U2 VU2 minus U1 VU1 is the equation. Now, for an ideal case, fluid enters radially with no whirl component. Since we are dealing with the centrifugal compressors, whirl at the inlet is considered as the 0. If whirl at the inlet is 0, then VU1 is equal to 0. If VU1 becomes 0 in this equation, then energy transfer becomes U2 VU2, wherein this term will be vanished. In the next stage, for maximum energy transfer from the impeller to the fluid, the blades are assumed to be radial. In the sense, in order to have the maximum energy transfer from the machine to the fluid, blade should be assumed as radial. If that is the situation, then U2 should be equal to VU2. VU2 is nothing but the tangential component at the outlet. So, U2 itself becomes VU2. So, now if I look on to the final condition, maximum energy transfer, look on to this, it is U2 VU2, here U2 itself is becoming VU2. So, maximum energy transfer will become U2 square. So, now if I consider the slip also into account, then E is equal to slip coefficient mu times of U2 square. Here this is without slip, here it is including the slip coefficient, that is nothing but mu. So, this becomes the final equation, theoretical or maximum work done on the air by considering the slip also. So, this is what is the energy transfer equation. If you are considering the slip, please consider this. If you are neglecting the slip, then please consider this. E maximum is equal to U2 square. So, this is what is regarding energy transfer. Next is we have one factor that needs to be taken into account, which is nothing but power input factor or work done factor, which is denoted by Xi. Why this factor has to be taken into consideration? We need to understand that first, because we need to supply certain amount of energy to the machine to impart energy to the fluid. That is what is power absorbing machine. We need to provide the mechanical energy to the machine, thereby the machine is going to provide the energy or transfer the energy to the fluid. It has to happen in such a way. Now, fluid is entering into the machine. If incoming fluid to the machine has certain amount of properties, say for example windage. If its wind is blowing, I mean the air is having the velocity of different values with respect to the time, then that needs to be taken into account. Then the fluid has to interact with the blades of the impeller. Then there comes the friction between the blades and the fluid, which is nothing but the disc fraction, and fluid has to move out through the casing. There comes the casing losses. All these factors will come into picture. So, in order to overcome all these factors, the power supplied to the machine is greater than that of the power that has to be actually supplied. In order to overcome this, I need to supply more amount of power to the machine than actually it is required. So, such a thing has to be taken into account by power input factor or work done factor. How I am defining the power input factor or work done factor? It is ratio of actual work supplied to the theoretical work supplied. This theoretical work supplied is the maximum value, which includes all these losses. In order to overcome these losses, what is the actual power that has to be supplied to the machine? That is there in the denominator. Then what exactly is required? What actually is required? That is there in the numerator. Numerator doesn't consist of any losses, and denominator consists of the power which is required to overcome the losses. So, now actual work supplied is denoted by E, and theoretical work supplied, we have calculated that over here. Theoretical work supplied or energy transfer is mu times of U2 square. I have written that mu times of U2 square over here. So, energy divided by mu times of U2 square is nothing but the Xi work done factor or power input factor. If you want actual work supplied, E is the actual work supplied or actual energy transfer. So, E is given by work done factor or power input factor Xi into mu into U2 square, which is nothing but theoretical work supplied. So, theoretical work supplied times of that of Xi is going to give us the actual work supplied, and this actual work supplied has to be expressed with the help of power input factor or work done factor. So, these two plays a huge role while taking the design of the compressor into the account. Okay, let us look on to few more equations. Very first one is overall pressure ratio, and the next one is loading coefficient or pressure coefficient. Now, come to overall pressure ratio. It is denoted by P suffix R, pressure ratio, where O stands for overall. So, overall pressure ratio. We knew overall pressure, overall work done by the compressor is given by difference between the enthalpies. So, here H02 is nothing but HO2, HO2 is nothing but enthalpy, overall enthalpy at the exit of the impeller minus overall enthalpy at the inlet of the impeller. 1 stands for inlet of the impeller and 2 stands for exit of the impeller. So, that enthalpy difference is going to give us the overall work done. So, now from the previous equation, E can also be written as xi mu U2 square. Then this is considered as work done per unit mass. Either I can make use of this equation or I can make use of this equation in order to look into the W per unit mass, work per unit mass. Now, there is no work transfer in the diffuser, in the next device, there is no work transfer which is going to happen. So, because of that, this 02 and 01 can also be written as difference between 03 and 01. Enthalpy difference between diffuser and the impeller inlet is also equal to enthalpy difference in the impeller itself, because in the diffuser no work is going to transfer. So, at the exit of the entire device, it is overall enthalpy 3, at the inlet of the entire device is overall enthalpy 1. Now, at constant pressure, the enthalpy can be given by Cp times of difference in temperature, Cp into total temperature at the exit of the diffuser minus total temperature at the inlet of the impeller. This is also equal to H02 minus H01, where H02 minus H01 is nothing but xi mu U2 square. That is what I have written over here. This equation has been written by comparing equation number 1 and 2. So, now I am with this equation. I will solve this equation for overall temperature difference at the exit of the diffuser minus overall temperature at the inlet of the impeller. So, I will keep this to the left hand side and then I will send the Cp to the right hand side. Then I will be available with this equation, and I will call this equation as equation number 3. Now, I have attained this stage. Now, I will come back to the one of the efficiency of the compressor, which is nothing but efficiency total, overall total efficiency to total efficiency, which is given by isentropic enthalpy rise to the actual enthalpy rise. Isentropic enthalpy rise is given by T03, overall temperature at the exit of the diffuser. It is denoted by dash minus overall temperature at the inlet of the impeller. So, this dash is the indication for isentropic phenomenon. So, here temperature at the isentropic work, here the ordinary temperature, which is nothing but the actual temperature. So, the same ratio, here it is isentropic enthalpy, here it is actual enthalpy. So, Cp gets cancelled with each other. If I move to the next step, it is temperature difference in isentropic enthalpy and this times of, overall efficiency times of this actual enthalpy rise temperature, T overall 3 minus T overall 1. Now, if I take the T01 common, or if I divide entire equation by initial temperature of the impeller, this becomes T03 dash, which is nothing but isentropic temperature, actual temperature at the impeller minus 1 divided by T01 into N total efficiency minus, into T03 minus T01. What I have actually done is, I have taken T01 common, or you can divide entire equation by T01. I will call that as equation number 4. I have T03 minus T01, I have called this as equation number 3, and I have T03 dash divided by T01 minus 1. I have called this equation as equation number 4. Now, by merging 3 and 4, we can look on to overall pressure ratio. What do you mean by overall pressure ratio? The initial device with which my concern is Impeller inlet is condition number 1, impeller exit is condition number 2. Next, the same condition number 2 satisfies the diffuser inlet, and condition number 3 is diffuser exit. So now overall pressure at the diffuser exit divided by overall pressure at the impeller inlet. So that is the ratio, overall pressure ratio, which is given by this term to the power of gamma divided by gamma minus 1, where gamma is the adiabatic index. So this is what is the overall pressure ratio that I was talking about at the initial stage. So overall pressure ratio, why I am calling it as overall pressure ratio? Because overall pressure at the exit of the diffuser divided by overall pressure at the inlet of the impeller. This ratio I was looking for. So this is what I need to attain into the overall pressure ratio in the compressor with the help of isentropic enthalpy rise as well as actual enthalpy rise. The next factor is loading coefficient or pressure coefficient, which is denoted by phi p. Phi p is nothing but again the same definition, is isentropic enthalpy rise to the Euler's work input. In the sense here, isentropic enthalpy rise in the sense it is the zero entropy enthalpy rise. No change in entropy is going to happen, divided by Euler's work input. What kind of work input that we are giving to the machine? We have the equation phi p is equal to Cp times of T overall at the exit of the impeller dash. Dash stands for isentropic temperature minus T overall at the impeller inlet divided by Euler's work input is nothing but U2 square. Now by using the isentropic efficiency definition, phi p is this isentropic temperature can be converted into ordinary temperature by including compressor efficiency, that is eta C Cp times of T02 minus T01. Here if I include the compressor efficiency, then this isentropic temperature gets converted into ordinary temperature. That is what I have done over here, divided by the same Euler's work input, which is nothing but U2 square. But actual work input that we have done in the previous equation, delta H naught, which is nothing but the overall difference in the enthalpy, which is nothing but Cp times of T02 minus T01, this much, Cp times of T02 minus T01, which is equal to E, which is equal to xi mu U2 square. This equation we have calculated in the previous equation. Xi mu U2 square, that is also considered as delta H naught. Now this Cp T02 minus T01 can be replaced by xi mu U2 square. This term is replaced by xi mu U2 square. Therefore phi p becomes compressor efficiency times of xi mu U2 square divided by U2 square. Now U2 square get cancelled in this step. The loading coefficient or pressure coefficient phi p will be compressor efficiency times of xi times of mu. It is the slip coefficient, it is the power factor, and eta C is the compressor efficiency. That is what is phi p. One such equation for phi p, that is pressure coefficient, is nothing but this. In the next stage we can express phi p, loading coefficient or pressure coefficient, in terms of exit blade angle beta 2 also. Please look into here, phi p, I have the equation for phi p. Phi p is nothing but isentropic enthalpy rise, which is nothing but U2 VU2, Euler's work input, which is nothing but U2 square. I have written the same dimension over here, same equation over here. So phi p, which is nothing but, I will cancel U2 with one U2, I will be remained with VU2 divided by U2. From the velocity triangle, we are very much aware that VU2 for the exit velocity triangle can be written as U2 minus Vf2 cot beta 2 divided by U2. So phi p will be U2 by U2 is 1 minus Vf2 divided by U2 times of cot beta 2, where Vf2 divided by U2 can be written as phi 2. So 1 minus phi 2 into cot beta 2, where phi 2 is flow coefficient at the exit, and its value is Vf2 by U2. So this is the another form of pressure coefficient or loading coefficient. First form is this, wherein all are coefficients, compressor efficiency, power factor, and mu slip coefficient. Second form is in terms of blade angle at the exit, phi p, which will be equal to 1 minus phi 2 times of cot beta 2. This is in terms of blade angle. So, these are the important equations that I will be using in order to solve the problems. This is what is for the today's session. We will meet in the next session. Until then, namaste.